So today we're looking at sampling distributions and two targets that are pretty fundamental ideas for our work with statistics and analyzing our data. Law of large numbers and the central limit theorem. Okay? Now, we saw this law of large numbers at the tail end of our unit on probability. We know that when we're talking about expected values or means, then we're talking about what we expect or anticipate in the big picture. I said that a million times during our probability unit, that probability is meant for the long haul. It's meant for the big picture. So when we're doing that example problem with like the average number of ice cream scoops from that ice cream shop, it was an expected value that over the course of the summer season, the average customer purchases 2.3 scoops of ice cream. That doesn't mean much on an individual basis because there's variation, there's variability. One customer purchases 1 scoop, another purchases 3, somebody else purchases 5. But across the big picture, across the entire day's worth of sales or the entire season's worth of sales, on average they're buying 2.3 scoops. So this law of large numbers allows us to speak towards the population. And that's what we care about. Remember, the whole purpose of statistics is to use this sample to say something about the population. And we don't care about, don't be disingenuous with this, but we don't care about the sample that we take. We care about how well that sample represents our population and that we get good data from this sample that describes accurately what's happening in that population. And this law of large numbers facilitates that. Secondly, this central limit theorem. This is like the big idea of statistical inference, in that we spent a good amount of time earlier this year talking about the normal distribution. And we said that the normal distribution works well for natural measurements. Okay, you're looking at the heights of a homogeneous population. They tend to fit this normal curve. Most people are around the mean in the middle. Very few extremely short people, very few extremely tall people. But there are a lot of data sets that don't fit that normal distribution. Okay? Well, we looked at the normal distribution because it was kind of easy and straightforward of the others to look at. But what this central limit theorem does is it allows us to look at non-normal data and normalize it. It allows us to make it fit that normal distribution. So we'll look at how that happens towards the end of the lesson today. Now, I will say in this lesson there's a lot of theoretical stuff that I'm trying to balance out by illustrating it with examples. Okay? Because that's what's meaningful, and that's what stands out for us here. So, kind of weigh these two separately, but we're starting out with a little bit of terminology here. We're talking about the sample versus the population. And we have two different words for our terminology. A parameter is a number that describes the population. Okay? Now, we don't typically know this because we're not doing a census usually. We're working with a sample. But when we're talking about a population's mean or a population's standard deviation, those values are parameters, not statistics. Now, notationally, we've already seen this. A population mean is represented by mu. Population standard deviation is represented by lowercase sigma. Okay? These are two parameters. Statistics are taken from samples. Okay? So when we're taking a sample and that sample has a mean, we represent that with x bar, and that sample's standard deviation is lowercase s. Now again, we saw that difference with the graphing calculator, if you're doing the 1var stats for a list of numbers, it gives you both sigma and s. And we had said that the difference is just dividing by an n versus an n minus 1. The two numbers are pretty much the same. But if that list of data was the entire population, you'd go with the sigma. If it was just a sample, which it usually is, you're going with s. Yeah? Now, conveniently, these letters match up. Okay? Statistics come from samples, S and S. Parameters come from populations. Okay? So you can easily correlate those words with the sets that they represent. Now, this is pretty straightforward common sense here. And we've been saying this. The process of statistical inference involves using information from a sample to draw conclusions about a wider or larger population. Now, there's no guarantee that what we get in the sample exactly matches what we get in the population. I've been saying this for a long time. We flip a coin 10 times, we expect 5 heads, 5 tails. But there's natural variation, there's variability across the samples. I could get 6 heads, 4 tails, 7 and 3. To a lesser extent, 8 and 2. It would be less likely, but it happens. There's variation in the samples. Now, what we are looking at today are these sampling distributions of the possible values, and we're performing an inference based off of those possible values. And what we can do to tie back in our probability, we can think of a statistic as a random variable because it takes numerical values that describe the outcomes of the random variable, the random sampling process. Yeah. So we can examine these probability distributions using what we've already learned. So, this law of large numbers. It says here, if x bar, that sample mean, is rarely exactly right, okay? Very rarely is it perfectly matching what we expect in the population, and it varies from sample to sample, okay? One sample might have this mean, the next sample we take has a different mean. Why is it nonetheless a reasonable estimate of the population mean? Well, the answer is this law of large numbers. If we're to keep taking larger and larger samples, that X bar statistic is guaranteed to get closer and closer to that parameter mu. Essentially, we're taking a limit. If you want to bring in calculus here, we're taking the limit of all of these X bar values as n, the sample size, approaches infinity. As that happens, that X bar is getting closer and closer to that population mean. Yeah? If you don't know anything about calculus, that's fine. But what this is saying is that the bigger the sample size, the better. The better that sample mean represents the population. Yeah? So what this law of large numbers is saying, you're drawing observations at random from any population with a finite mean mu. As the number of observations drawn increases, the mean X bar of the observed values gets closer and closer to the population mean. Now, a sampling distribution, it differs from a population distribution. Okay? Back in September, October, forget exactly when this was, we were looking at population distributions where you're comparing an individual to the rest of the population. We did this for like IQ scores, we did this for standardized test scores, things like that. where the mean goes at the center of that curve, and then the standard deviation is our step size that goes above and below. And we used z-scores to help give us some perspective in terms of, well, we're this far away from the mean, and we have accompanying probabilities. Okay? This percentage of the population is below us, this percentage of the population is above us. Okay? And we use technology, GeoGebra, graphing calculator to assist us with that. Now, again, with this, we're not really looking at the population. We're looking at samples. So if we took every one of the possible samples of a certain size, calculated the sample mean for each one, and graphed all of those values, we'd have a sampling distribution. Okay, so think about what's happening. We have a population, that population has a mean. Let's say we're taking samples of size 25. Okay. We're taking every single possible sample of size 25 in that population. And what's happening is the average of those averages becomes this population mean. Essentially saying that these X bars become that population mean. The population distribution of a variable is the distribution of values of the variable among all the individuals in the population. That's what we're saying up here. But the sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of the same size from the population. This is where we need to be careful, because they look essentially the same. We had a mean up here at the center. We have the population mean still here at the center of our sampling distribution. But this time, our standard deviation is not the same as what we had with the population distribution. Okay? It has our word of caution down here. The population distribution describes the individuals that make up the population, but sampling describes how a statistic varies in many samples from the population. We're getting too theoretical right now. Okay? We need to look at an example. Okay? Now, this example is using proportions. Okay? For right now, we're concentrating on means, but it helps illustrate what's happening. This is kind of similar to a coin flip. Okay? But instead of heads and tails, it's saying 50% of the time you get blue, 50% of the time you get red. Okay? That's our expectation. Our parameter is that P, population proportion, is 50%. Essentially the same as the mean. We're going to take a bunch of samples of size 20, it's an N, and we're going to keep track of how many reds we get. Okay? So our first sample of size 20, we got 8 out of 20 as red. That's 40%. That's a little bit lower than what we expect. Our next sample of size 20, we got 11 reds. That's a little higher than what we'd expect, 55%. Our next sample, 13 out of 20 are red. That's higher, even more so than what we'd expect, 65%. And we're making a distribution. Essentially, we could make like a dot plot here and stack up these probabilities. We had one that was 40%, so one of them right there. We had another that was 55% right there. We had another that was 65% right there. Okay. Most of our samples give us something either at or around 50%. We had a few extreme values. One of our samples was only 15% reds. 3 out of 20. Another one was 80% red, 16 out of 20. But those are few and far between. Most of the samples are right around the center, and it fits this sampling distribution. Okay? Not the population, but the sample. Here's another one. Let's say there's a nationwide weight loss clinic where people go away, they're all motivated to lose weight. They go away for 10 weeks and they help you get your diet straightened out, they help you develop proper exercise habits, that sort of thing. Now, this goes across a large number of people. Unknown to us, the entire population of participants, there is an average amount of weight lost across everyone. And that is 8 pounds. This is like if we did a census of every single participant. The average weight lost is 8 pounds. The standard deviation is 5 pounds. Okay? So there's some variability here. Not everybody loses 8 pounds. Some people lose more, some people lose less. Now, from this, these are population values. We could look at a population distribution and see how we compare. Right? The mean amount of weight lost is 8 pounds, but a standard deviation of 5. 13, 18 going up. Going to the left, 3 pounds, negative 2 pounds going to the, or this was to the right, this is to the left. Okay? And because this is the normal distribution, we could use our empirical rule. We went 2 standard deviations to the left, 2 to the right. This means that 95% of the participants in this weight loss clinic, we would expect to lose between negative 2 pounds, which is actually a gain of 2 pounds, and 18 pounds. This is how the individual compares to the population. It's a population distribution. This is nothing new. Okay? We did this earlier in the year. But from this population, we are going to take random samples of size 25. And here are a few of those theoretical samples. Okay? Our first sample. You can see we have 1 pound lost, 1 pound lost, 2, 3, 4, 4, 4, 5, 6, 7, 7, 7, and so forth. Okay? All the way up through 16. That sample has an average, a mean of 8.32 pounds. So a little bit above the population's value. The standard deviation, 4.74, okay, slightly below that population's standard deviation. These are statistics. They are sample values, sample means, x bar 1, x bar 2, 3, and 4. And these are sample standard deviations, S1, S2, S3, S4. Okay? Each sample gave a different sample mean. They're all pretty close to 8. And the sample standard deviations are all pretty close to 5. And again, just kind of backpedaling here, we can analyze this a little closer. Like our highest standard deviation of 5.93 pounds was in the 4th sample. Look at that 4th sample. We had weight loss ranging from negative 3 pounds. We had 3 participants gain weight at this weight loss clinic. And on the upper end, we had somebody lose 19 pounds. So that range there of 22 pounds was pretty spread out. There was a lot of variation there, so we have this higher standard deviation. Compared to sample 1, its standard deviation was 4.74 pounds. Nobody gained weight. It ranged from 1 to 16. So that had a range of only 15 pounds. So that standard deviation is smaller because there's less variability. Okay? Now, here are our 4 samples. We want to be able to use this data to say something about our population. So we'll come back to this example in a few minutes. Now, with these sampling distributions, if we were to take many of these random samples from a population, sampling distribution of the sample mean is centered at the population mean. Okay? The average, essentially, the average of all of these averages should become mu. So, at the center of this sampling distribution, we are still going to have mu. But the standard deviation of this sampling distribution, there's a slight difference in our calculation of the standard deviation. It's now our sigma, our population standard deviation, divided by the square root of the sample size n. So, the mean hasn't changed. We say that's an unbiased estimator of the parameter mu, because they're the same thing for the sample and for the mean. Or, I'm sorry, the sample and the population. But because its standard deviation is sigma over the square root of n, the averages are less variable than individual observations. And the results of large samples are less variable than the results of small samples. Okay? So here's what you want to remember. This is for the population distribution. Okay? It fits a normal curve for n with a mean of mu, standard deviation of sigma. But the sampling distribution, it also fits a normal curve, mean of mu. Its step size is sigma divided by square root of n. Okay? We need to look at these back to back, and that's what we're going to do. Okay? In a second. Let me finish a little more theory here. This central limit theorem allows us to pull things together, even when that original distribution for the population is not normal. Okay? Because most population distributions are not normal. Okay? If you were to, I don't know, wait for your bus at the bus stop on a typical morning, and you're to keep track throughout the week, throughout the month, throughout the year of how long you wait for that bus. Okay? You get there at the same time every day. Your bus is supposed to come at that same time. Okay? You might wait for 1 minute, you might wait for 30 seconds, you might wait for 2 minutes. But most of those waiting times would probably be pretty short. At least, hopefully, they'd be pretty short. But then maybe there's a day like today where the weather's not great in the morning and the bus gets delayed. So there are some days when maybe you're out there waiting for 10 minutes, 12 minutes, 15 minutes. But hopefully those are few and far between. But that distribution might look something like this. Clearly not normal. Okay? But most of the days you have wait times of 1 minute, 2 minutes, 3 minutes. And you have very few days where you're waiting 10 minutes. Okay? So that's not a normal distribution. And not all of our data sets, most of our data sets from populations are not normal. But what the central limit theorem does, says it is a remarkable fact that as the sample size increases, the distribution of sample means changes its shape. It starts to look less like that of the population and more like that of a normal distribution. And I have a simulator that I'm going to show you this in action tomorrow. Okay? But we don't have to have a normal set as long as that sample size is large. Okay? That's always important. We want the bigger the sample size, the better. But here's another reason why it's essential. Okay? The central limit theorem says you take a simple random sample of size n from any population with a mean of mu and a finite standard deviation sigma. This theorem says that when n is large, the sampling distribution of the sample means x bar is approximately normal. Okay? Where mu is that population's center, or that sampling distribution center, I should say, and sigma over the square root of n is the standard deviation. And it allows us to use normal probability calculations, z-scores, to answer questions about sample means from many observations, even when the population distribution is not normal. Okay? Something like this. Here's just a picture of some people. Okay? There's your population. Again, one sample has its own mean, another has its mean, another has its mean. Okay? But they're fitting this curve. Okay? All of those sample means fit this normal distribution. Let's go back to our weight loss example. Again, we had a mu of 8, a sigma of 5, and we were taking samples of size 25. So, the potential sample means represented by a bell-shaped curve with a mean of 8 pounds. The standard deviation looks like this. Again, sigma over the square root of n, 5 divided by the square root of 25. Square root of 25 is 5. 5 over 5 is 1 pound. So this sampling distribution looks like this. We have our 8-pound population mean right there at the center. That doesn't change. But the new standard deviation, 9, 10, 11. We're going to the left, 7, 6, 5. And because this fits the normal model, use that empirical rule, 68, 95, 99.7. 95% of our data, 95% of our sample means should be between 6 and 10 pounds. Right there. Almost 100%, 99.7, is between 5 and 11 pounds. Compare this back to our population. Remember, our population, it had 8 at the center as well, but its standard deviation was 5, so this was 13, this was 18, this would have been 23, but we didn't even take it out that far. This was 5, this was 3, negative 2, negative 7. Population versus sample with size of 25. Do you see the difference between these two? Okay. Think about how and why these differ. In the population, you're looking at an individual person. It's possible that you could get some rock star going to this weight loss clinic and losing 23 pounds. They're at the far end of this curve. We know that extreme values are unlikely, but they happen. But on the sampling distribution, 3 standard deviations to the right is only 11 pounds. To get 23 on this sampling distribution, that would mean that you have a sample that would average a weight loss of 23 pounds. So you're not just getting the random person who loses 23 pounds, but instead you have a sample of 25 people where the average in that sample is a weight loss of 23 pounds. That would be incredibly rare. The sampling distribution is always going to be less variable than the population distribution. Does that make sense? because these numbers down here are the averages for the sample. These numbers here are the individual weight loss values. Okay? On the flip end, yeah, maybe you have somebody who goes to this weight loss clinic where they're concentrating on your diet and your exercise program, and they gain 2 pounds. It's unlikely, but it happens. But to get an entire random sample of people who would gain 2 pounds, that would be very unlikely. Okay? Because you're going to have some people lose the weight. Okay? That pulls that sample mean closer to that expected value, that expected mean. Now, this was a sample of 25 people. We said that the bigger the sample size, the better. So what if we were to inflate that sample size now to 100 people? Only one thing changes, and that's the standard deviation calculation. We know that the center of this distribution is still going to be mu, 8 pounds, but now sigma over square root of n, 5 divided by square root of 100, square root of 100 is 10, 5 over 10 is 1/2. Now our step size is 0.5. So one standard deviation above is 8.5, then 9, then 9.5, going to the left, 7.5, 7, 6.5. Now we've got a 95% chance that our sample mean is going to be between 7 and 9 pounds. Previously, we were 95% sure that our mean was going to be between 6 and 10 pounds. Think about this. The bigger the sample size, the better. If we see this trend, this mean happen across a larger group of people, it's 4 times the size. We are more certain that this is truly what's happening in the population. So we can narrow in our boundaries. Okay? Before, we were only 95% sure it was between 6 and 10 pounds. But now when we see this happening across 100 people, we'd be 95% sure that it's between 7 and 9 pounds. Okay? And if we kept inflating that sample size even more, these boundaries would be narrowed in even more, closer and closer to that population mean of 8. Okay? Larger samples tend to result in more accurate estimates of population values than do smaller samples. Questions so far? All right. Let me give you one other example here. It says, based on service records from the past year, the time that it takes a service technician in hours to complete preventative maintenance on an air conditioning unit follows a distribution that is strongly right skewed. Okay? Like this. It's kind of like waiting at the bus stop, where hopefully most of our service calls are on the lower end. Doesn't take much time to resolve the issue, but occasionally there's something that you can't figure out the problem, or you can't get the problem fixed, and it takes a long amount of time. Okay? Clearly that's not normally distributed. So for this data set, the mean time is 1 hour, and the standard deviation is also 1 hour. Now, your company is going to service a random sample of 70 air conditioners, and you've budgeted 1.1 hours per unit. Okay? So essentially 1 hour and 6 minutes per unit. Okay? A little bit of a buffer. Okay? You want to make sure that most of your service calls fit within that time limit. Will this be enough? Well, the central limit theorem states that the sampling distribution of the mean time spent working on the 70 units, okay, it has a mean of 1 hour. Okay, we can start to visualize this sampling distribution. Okay, even though our population distribution has no resemblance to a normal curve, we know that our sampling distribution will. So 1 hour right there at the center. Standard deviation calculation looks like this. 1 over square root of our sample size of 70, you can trust me with the math, gives you an answer of about 0.12. So our step size on the sampling distribution is 0.12. So this is 1.12, 2.24, etc. Going to the left, 0.88, 0.76, and so forth. Now, rather than the empirical rule to say 68, 95, 99.7 in this case, let's do a z-score calculation because we are specifically interested in allotting 1.1 hours per service call. So remember our z-score calculation, we take our value minus the mean divided by standard deviation. And the z-score will tell us how many standard deviations we are away from that center. And from there, we can go to our z-score chart, or more practically, graphing calculator, normal CDF, or GeoGebra to get these probabilities. What proportion of that population is less than this value or above this value? So in this case, remember, 1.12 was 1 standard deviation above. We are at 1.1, so we are just a hair shy of 1 standard deviation above. So we work this z-score equation out. If we're doing it by hand, we are 0.83 standard deviations above the mean, which we could look this up on our chart or let the calculator, GeoGebra, do this calculation for us. We have about 80% of our service calls will take less than that amount of time for our sample of 70 air conditioners. On the flip side, about 20% of our samples would have an average call time above the 1.1 hours, the 1 hour and 6 minutes. Okay? So from here, we could kind of weigh that out. Okay? You actually perform this analysis. You take your sample of 70. Okay? If you're to get something that was longer than 1.1 hours, well, there's a 20% chance of that happening. Okay? 1 in 5. On the flip side, 80% of our samples of that magnitude will be less than the 1.1 hours. We kind of showed this by hand, but again, you can clearly go to GeoGebra, put the mean of 1, standard deviation of 0.12, and get these same things. It doesn't change. Use the tools that are available to you. That's what I was saying at the beginning of class. Questions right now? All right, last slide. Just kind of wrap up here. We've looked carefully at the sampling distribution of a sample mean. And however, any statistic we can calculate from a sample will have a sampling distribution. And it's up to us to kind of look at that distribution and infer some conclusions about that. The sampling distribution of a sample statistic is determined by the particular sample statistic we are interested in. Distribution of the population of individual values from which the sample statistic is computed, and the method from which the samples are selected from the population. So that's kind of saying that we've been looking at simple random samples. Our other random sampling techniques should still follow these rules. The sampling distribution allows us to determine the probability of observing any particular value of the sample statistic in another such sample from the population. Again, kind of ties back to why we looked at probability, allowing us to quantify the chances of events like this happening. Anybody have any questions right now? Let me cut this off here.